Good evening, everyone. Am I audible clearly? Yes, am I audible clearly?
Yeah, your voice is clear.
Okay. So let's begin today's session. So we are at week 9, starting with the first problem that we have today. So in this particular problem, there is a differential amplifier configuration you can see, right? So this is a differential amplifier with two PMOSs. So in this particular question, what is it given that Kw by L is 2 milliamperes per volt square, VTHP is minus 1 volts, lambda is 0.01 volt inverse, RD RD is RD1 and 2 are 1.6 kilo ohms, RT is 1 kilo ohm, VDD is 12 volts, V in see this DC voltage is 5 volts. Now for this particular circuit, find the maximum output voltage swing towards the negative side of the sinusoid. So that means here this V out will be fixed at a DC voltage, right? So it is like VDD to ground rail. In between somewhere there will be V out DC voltage because of the DC biasing. Now over this, when you apply an AC input, you will see an AC output as well, right? Oscillating to and fro from that DC level. So the idea is you have to find this swing that is towards the negative side. So from the DC level, what is this particular swing? In the negative side, this is what is asked in the problem. So first of all, what are the things that we know? So how would you find this voltage? What is this voltage V01 and V02? If we observe very carefully, what are these voltages?
Output voltages.
Output voltages, but how would you find it, or how can you represent V out 1 and V out 2? So isn't it the voltage which is dropped across this RD1 and RD2 because there is a ground which is connected there? So whatever is the voltage drop across RD1, can I name it as V02? And similarly, the drop across RD2, I can name it as V01. Can I do that? Are you getting my point? So how would we write? Yes, so V01, we can write it as like the current flowing through this, let's say I1, okay? And the current that is flowing through this is I2. So if I'll write V02 is equal to I1 into RD1 and V01 equal to I2 into RD2, is it correct? Come on, is it correct? Yes. So now we know that, okay, if we find the currents, we know the resistance. So we can simply write like current into voltage will give us the, like current into resistance will give us the voltage. Correct? So how to find this current? So you see there is a PMOS transistor, right? Above these RD1 and RD2. And since this PMOS and your RD1 are in series, so same current will flow through it, right? So if I'll name it as ID1, ID2, so my ID1 is equal to I1 and ID2 is equal to I2, right? Correct? If you won't respond anything, I'll consider you understand it. Else, if you have any doubts, please unmute yourself and answer. Okay? Like ask your doubts, whatever it is, and I'll answer. So let's move on. So we know that the currents through the transistors is the current that is also flowing through the load resistors or drain resistors RD1 and 2. And if we find that current, we can find the voltages and hence we can also find the swing. So here, how do we write ID1? Since it is a PMOS transistor, so it will be kW by L, kW by 2L, VSG minus VTH of whole square. So this is the current that is flowing through the transistors M1 and M2. So here this is source, gate, drain. We also know that the current flowing through the transistor RT, like IR, is equal to ID1 plus ID2. Correct? For the transistors, we don't know this particular point voltage, right? X, Vx. If we would have known this potential at S, like X node, so which is the source for the transistors, we would have simply got the current through the transistor. But since we don't know the potential at this point, so what we will do, let's equate the currents for like the current flowing through your RT transistor and these two transistors. Now we know that since it is a matched system, so 2 times of MOS current will be equal to your IR. So if I write it down, so it is 2 kW by 2L VSG minus mod VTH whole square is equal to VDD minus Vx or Vs, anything is fine, by RT, right? So here 2 cancel. Vs minus Vg minus VTH square equal to 12 minus Vs by RT. RT was 1 kilo ohm. So 1K. If I multiply it this side, so it will simply become 2 volt per second square. Vs minus Vg was already known, right? Vg is 5 volts. We are analyzing the DC currents currently. Minus VTHP is 1 whole square equal to 12 minus Vs. So correct? Now if we solve this equation, we'll get the values for Vs, right? So what is the value of Vs that we are getting? Why we are calculating Vs? Because the moment we get the Vs, we can simply find the current, and through that we can find the V out. So that's why Vs is very important. So what is the value of Vs that we are getting?
7.5 and 4.
Uh, how much is it?
7.5 and 4.
Vs we are getting is 3.5 and 4.
7.5.
7.5, right? Yeah. 7.5 and 4, correct. Okay, now we have got two values, right? Vs as 7.5 and Vs as 4. Now which one is correct? So is Vs 7.5 or is it 4? For a PMOS, what is the condition for turning on your transistor? VSG should be greater than VDHP, right? Mod. Correct? Now say your Vs is 4 volts, Vg is 5 volts, your VSG is how much? -1, which is less than 1 volt. So this cannot be the case. Hence, your Vs is 7.5 volts, right? So with this answer, what we'll do, we'll find the current. So the current is kW by 2L VSG minus VTH whole square, that is 2 millivolts per second square by 2 into 7.5 minus 5 minus 1 whole square, that is 1.5 square. So what is the current that we are getting? 2.5 milliamperes. Correct? The current is 2.25 milliamperes. Now we have got the current. We know V naught 2 is ID into RD1, which is 1.6K. So V naught 2 is 2.25 into 1.6K milli. So this will be 0.6 volts. So the voltage that we are getting is 3.6 volts. This is what corresponds to the lower limit of your swing. Okay, so this is 3.6 volts. Now moving on to the next problem. So in the same figure, you have to find the CMRR of the same circuit. So we know that CMRR, what is the formula for CMRR? AD by ACM, correct? What is the formula for AD? How do we write AD? Yes. Simple, right? GM into RD, no? We simply write AD is GM into RD. Now GM is kW by L, V is G minus VTH, which is 2 millivolt per second, 2 millisecond per volt square, 2 milliamperes per volt square into Vs was 7.5 minus 5 minus 1. So that is 2 milliamperes per volt square into 1.5. So Gm is 3 millisiemens. And what about Rd? So again, since we are performing our half circuit analysis, so this is source, gate, drain. So what is the Rd? Which is Rd1. So Ad is Gm into Rd1. So that is 3 into 1.6, which is 4.8. Correct? So this is the Ad that we got. Now the next thing is ACM. So like for AD, as we have the formula, similarly for this type of circuit, if we analyze, the formula that we get for ACM is Gm into Rd upon 1 plus Gm into 2 times of Rt. Okay. So this is the formula that we get for by analyzing this particular circuit. Now substituting simply the values of Gm, that is 3 millisiemens, Rd 1.6, 1 plus Gm, that is 3 millisiemens, into 2 into Rt is 1K. So this is 4.8 by 7. 4.8 by 7 is the ACM that we got. Now for CMRR, we have AD by ACM, that is 4.8 by 4.8 by 7. So CMRR is 7 volt by volt. So how much is the CMRR in dBs? Yes, how much is it in dBs?
$16.9.
How much?
16.9.
16.9, right? 16.9 dBs. So this is the CMRR that we are getting for this particular circuit. Now, before moving on to next set of problems, let's have a small discussion based on capacitors, because the next set of problems that we'll be solving are based on capacitors. So as we already discussed, that in a MOSFET, let's say it's an NMOS, gate, drain, source, what are the capacitors that we have? Yes, what are the terminal capacitors that we have? Which we name in terms of terminals. CGD, CGS, let's say there is a body terminal also, CDB, CSB, correct? Now depending on the condition of source and body, we might or might not have CSB. Now if we look at the types of capacitors, so these are CGS, CGD, CDB, CSB. These are terminal capacitors because we are talking in between the terminals. Now, if we say what are the types of capacitors, then what are the types of capacitors that we have? So for simplicity, let's say if I draw if I draw a MOSFET with this is source, drain. Gate. So okay, by looking at this particular MOS structure, can you say what are the different types of capacitors that we observe? What is capacitance, first of all? dq by dv, right? Wherever there is a change in charge, for change in voltage, we call it as capacitor. So first of all, if you observe very carefully, whenever you change, let's say this is grounded, okay? This is also grounded. This is also grounded. So the only potential that we are applying is at gate. So what happens when we only apply the voltage at gate? The charges at the surface change with the applied voltage, correct? Right? There will be a change in charge due to the applied gate voltage, correct? So this particular capacitance is known as Cox, which is given by epsilon by D. Depletion length, whatever is the depletion length, into epsilon of that particular material. So we call it oxide capacitance or gate capacitance. Now, this is between your gate and substrate. But if you observe very carefully, there is like this gate has an overlap area also, right? On source and drain side. So this will correspond to similar oxide capacitance, but we call it overlap capacitance, COVS or COVD. This is again due to the oxide that is present, but it is overlapped over your source and drain. We will also like name it as epsilon by D. It is like similar capacitance, similar type of capacitance. This is one type of capacitor first. So it is gate capacitance. So if I name it as A, B, and these come under gate capacitance. Now after this, once you apply your gate voltage, the next thing you do to get current is apply your drain voltage, right? So the moment you apply your drain voltage, you will have the change in charge configuration near your PN junctions, right? Here, because of reverse bias, you'll start seeing a depletion region forming. And here also, it will be forward biased, but still you will see a small depletion region because of this PN junction which is formed over here. So these two will also correspond to the capacitances. And we call these capacitances as junction capacitances. These are formed due to the PN junctions which are present over there. Okay, so this is due to PN junctions in the device. Right? So when we say terminal capacitances, then we are only talking about externally between the terminals. Okay, what is the capacitance that we are getting? But where do these capacitances actually come into picture? These are coming because of either the gate capacitance or the junction capacitance. Okay?
What
Yes.
capacitance means epsilon A by D. No?
Yes, but
No,
in
not
our
concept.
case, we so these all capacitance are per unit area capacitances. So when we talk in devices, so we talk about per unit area capacitance. So capacitance per unit area. So whenever we calculate our capacitances, you'll observe that the unit is also uh, like farad per meter square, farad per centimeter square, farad per micrometer square. So it is always per unit area capacitance is what we are talking about. Okay, but that's a good point, and you have to keep this in mind that this is per unit area capacitance. Okay. So now, yeah, with this basic discussion, let's move on and solve the problems based on these capacitor concepts. Okay. So starting with the first problem on this particular concept. So here we have a CMOS inverter which is designed below. The length of both NMOS and PMOS devices are 0.18 micro. Ln equal to Lp equal to 0.18 micrometer. The width of NMOS and PMOS are Wn is 1.8 micrometer, Wp is 3.6 micrometers. So what is the reason that we have kept the length of the two devices equal but the width of one is double to the other?
Mobility of charge
Sorry?
due to mobility of charges.
Yes. So when we are making a device, see, we always say that when there is like there are two transistors and they are in series, they have to carry the same current, correct? So for the same current, we know that the mobility of holes and electrons are different. We consider it on average to be double. Somebody is unmuted, so it's giving noise. Maybe you can mute yourself or yeah. So, um, it's unmuted. Okay. So what I was saying is, yeah, so since the mobility difference is there, so that's why to make your device have that current carrying capability, we increase the width so that we can get equal currents in this type of circuits where they are in series. Now, it is given like for NMOS, ND is 0.8 10 to the power 17 per centimeter cube. Na is 6.2 into 10 to the power. Okay, per centimeter cube. For PMOS, Na is 1.7 into 10 to the power 17 per centimeter cube. Nd is 10.9 into 10 to the power 17 per centimeter cube, respectively. Further, the depth of the doping for source and drain are 1 micrometer in both of them, and the length. So, doping, what they are talking about is this depth and this length. So, depth is d of uh, source equal to d of drain. Depth is 1 micrometer. and the length of source and drain is 0.18 micrometer. So this is L. Capital L of S, capital L of D is 0.18 micrometer. So these are the informations that are given. Now if the voltage at output X bar is zero point 0.9 volts, so this is source gate drain, this is drain gate source. So basically X bar is 0.9 volts. That means your VD is at 0.9 volts. Now for this, what is the total junction capacitance between the output node and ground? The working temperature is 300 Kelvin and we have to give the answer in femtofarads. So for your when you have 0.9 volts at your drain, that means in case of PMOS, your VSD is 0.9 volts. In case of NMOS, again your VDS is also 0.9 volts. So there is certain amount of voltage that is being dropped across your transistors, and let's see how it will change your capacitances. Okay. So first thing is, we know that we have to calculate the capacitances. So if we observe very carefully, there is definitely source and drain like capacitances, junction capacitances are present, correct? So how to calculate junction capacitance? The formula for junction capacitance at zero bias. And junction capacitance is between either source or body or drain or body, right? So the potential that we are talking about, so this capacitance will be influenced because of your source, VSD, source drain voltage. So the junction capacitance, the formula for junction capacitance is Cj0 root under epsilon Q Na Nd upon 2 Na plus Nd into VBI, that is built-in voltage of that particular junction. So, and this is epsilon, so let's say it is epsilon silicon, considering a silicon transistor. So epsilon silicon is 11.8 into 8.85 into 10 to the power minus 14. This is in CGS units, okay? Now, so in this particular formula, we know epsilon, we know Q, we know NA, for both NMOS and PMOS. What we don't know is VBI, correct? The junction potential. What is the built-in potential of that junction? So how do we find VBI? It is by VT ln NAND upon NI square, where VT is KT by Q, which is ideally 26 milli. How much is it considered? Yeah, 26 millivolts, which is 26 millivolts at 300 Kelvin. Now Ni is 10 to the power 10 per centimeter cube for silicon. So for NMOS and PMOS, we will find this built-in voltages. Okay. So that is Vn is 0.026 ln NaN NDN upon Ni square. So if we substitute the values, like let's substitute it rather than writing. Almost 0.8 and 6.2. 0.8, 6.2 into 10 to the power minus 34 by Ni square, that is 10 to the power 20. So what is the value of Vn that you are getting? What is the value of Vn? Yes, can you please calculate? Similarly, we will go for 1.7. Yes, what are the values of Vn and Vt that we are getting?
For Vn, I am getting minus 3.19.
How much?
Minus 3.19. Negative.
So for NMOS, the value you should get is 0.879 volts, and for PMOS, the voltage will be 0.914. Nobody is getting this? Okay. So what is the values that we are getting by substituting these? The values that we are getting are actually like for this particular case, we are getting it as 0.7965 volts, right? Minus 0.7965 volts. And for this other one, we are getting as 0.7, how much was? So somewhere near that. But the values that we should get is 0.879 and 0.914. Now see,
Ma'am,
yes,
Ni square minus 20.
uh, where?
It's 10 power 20.
Oh, ये plus होगा ना? So this will also be plus 17 plus 17, right? Yes, yes, it will be plus plus. So it is plus, and it is point, yes. So okay, so we wrote it down negative, right? No, no. So concentration is positive, right? 10 to the power plus 17 and 10 to the power plus 10. So powers will be in positive, and hence we will get 0.879 volts for N type and 0.914 volts for PMOS. Okay, yeah, it is plus. So this is the voltages that we are getting for these junctions, considering that there is no bias. So this is zero bias, 0, 0, 0, 0. So the bias voltage, or you can say like built-in voltage, built-in potential with zero bias, like ideally because of the PN junction that is formed. So the built-in voltages for NMOS and PMOS at 0 volt VDS, 0 VDS is this much. So now the capacitances that we get at 0 due to N would be like when we substitute this V naught N in the formula. So epsilon silicon Q Na Nd by 2 Na plus Nd into V naught N. We'll get a junction capacitance for N. Similarly for P we will get junction capacitance for P Nd by 2 Na plus Nd V naught P. And the junction capacitances that we are getting are 8.2 into 10 to the power minus 8 farad per centimeter square, and this is 11.817 into 10 to the power minus 8 farad per centimeter square. This is for zero potential. Now when we apply the potential, so junction capacitance with bias voltage, the formula changes to C junction or Cj will become Cj naught by root over 1 plus VDS, let's say VDS by V naught or VBI, or what we mentioned VN naught or VB naught. So this is how the formula will change. So for, let's say we are writing for junction capacitance of N. So the formula will be like this. Now we know VDS for NMOS is 0.9 volts. VN naught is 0.879 volts. So the junction capacitance is Cj naught, which was 8.2 into 10 to the power minus 8 farad per centimeter square by root over 1 plus 0.9 by 0.879. Similarly, for PMOS, it will be Cj naught P by root over 1 plus VSD upon VP naught. So that is, here VSD is again 0.9 volts, VP naught is 0.914 volt. So CJP will be 11.817 10 to the power minus 8 F square upon root over 1 plus 0.9 by 0.914. So this is the volt capacitor that we get, but this is per unit area capacitance, right? As I already mentioned, the capacitance is per unit area capacitance. But if you want to calculate the total capacitance, how would you calculate the total capacitance? it is C junction into area. You'll get capacitance, right, in farad. That is in farad per centimeter square. So here you should write your area in centimeter squares. Now, let's see how you will write the areas. Like what are the dimensions that will come in the junction capacitance. Okay. So first of all, when we are talking about junction capacitance and the transistor is in saturation region, that is, there is very high drain voltage. Your majority capacitance comes due to your drain voltage. So the majority capacitance that you see will be due to the reverse bias drain capacitance. So drain side, if we observe, here you will have your drain, right? This is drain. This is drain. So this dimension was given as LD. This was mentioned as D of D. So DD, LD, yeah. This is DD, this is LD. This is W of your transistor, width of the transistor. Correct? And so yeah, for a cube or for a cuboid, if we know the three dimensions, we can write the area, right? So now what are the surfaces at which you will see your junction appearing? So if we want to calculate the area of junction, to be specific, drain junction, what is the area? First of all, your this surface, that is into the plane, which consists of your depth and width of the transistor, right? That surface, depth and width of the transistor. So area will be D of D into W plus, now this surface is done. Next, which surface will come into picture? This surface will come into picture, right? The faces, like the drain depth into your length of the junction. Depth into length of the junction, which is this plane and the other plane. For this particular cuboid, this plane, face 1, and the backside face, that is face 2. So these two faces will also have your junction. So it is 2 times of LD into DD. Now third, you will have a junction which is at the bottom, right? So it will consist of your LD, that is length of your junction, and the width of the transistor, so the bottom face. So LD into W. Any other faces do we need to consider? Yes, any other phase that we need to consider? So what about this side face? What about the side face? Will it come into picture or not?
2DD into W.
DD into W, right? So there will be another factor which will be because of this DD into W. So here it will be 2 times. So if we observe very carefully, we have a total of 6 faces, right? So the first face, which is the front one, the opposite one is 2. This side face, which was with DD and W, this is phase 3. The opposite to that one is phase 4. Then there is a bottom surface, which I am naming as phase 5, and the top surface is phase 6. Correct? Now the question is, how many faces will have junction capacitance? Or if I change that question or tweak it a little bit, how many junctions or how many faces will observe a PN junction forming over there?
I
What about the top surface? Will there be any junction capacitance or any junction forming at the top? Phase 6. Yes, will there be any junction at phase 6? What do you think? Because we have already considered 5 faces, right, till now. All the 5 faces are done. Front, back, both the sides and bottom. What about the top surface? Top face? Is there any PN junction forming? There won't be any PN junction, right? Because at the top, what you will do at the very top of your, let's say, drain, you will deposit a metal and you will take a contact over there. So you will not have any PN junction forming there. So there won't be any junction capacitance at that particular phase. So we'll only see junction capacitance due to these 5 surfaces of your drain. Now, if we simply write it down, like W was how much? W, and let's say if we are writing it for NMOS, 1.8 micron. 1.8 micrometers. This is for NMOS. Plus 2 times of 0.18 into 1 plus 0.18 into 1.8 micrometers. And similarly, we can write it for PMOS. So for NMOS, the area is 4.284 into 10 to the power minus 8 per centimeter square. And for PMOS, the area is 8.208 into 10 to the power minus 80 per centimeter square. Now we know the areas, we know capacitance per unit area. So if we want to write like the total capacitance, how would we write the total capacitance? So it will be C junction, CJN into area of NMOS plus CJP into area of PMOS. So the final capacitance that we get after calculating is 9.199 femtofarad. Femto is 10 to the power minus 15, right? So this is femtofarad. So this is the total capacitance, or if we say to be very specific, the total junction capacitance that we see in this particular transistor. Okay. So this is the total junction capacitance, because we were asked to calculate the total junction capacitance between the output node and ground. So output node and ground, the terminal that appears is drain, and that's why we calculated the drain capacitances. Okay. Now moving on to the next problem for the same circuit again. Now in this particular circuit, let me So in this similar circuit, the question is, let's say the X is 0 volts. So this X is 0 volt. What is the total junction capacitance between the output node and ground? Give your answer in again the femtofarads and with the same temperature. So if it is 0 volts, we know that this is an inverter circuit, correct? When PMOS and NMOS are connected in series with same inputs being provided to PMOS and NMOS, so that configuration is basically an inverter, right? So for an inverter, if you give 0 at input, what will you get at the output? You'll get VDD as the output.
1.
Oh, sorry.
Yeah.
So
I
it is
got it.
1.8 volts. So now you are getting 1.8 volts at your drain. So that means if for PMOS, if I'll observe, my VSD is how much? 1.8 minus 1.8, that is 0 volts. So for the PMOS, my VSD has turned down to 0. Similarly, now if I'll calculate for my NMOS, my VSD is how much? 1.8 minus 0, that is 1.8 volts, right? So what will change over here because of these potentials? The value of junction capacitance will change, right? So again, we'll use the same formula. It's just that now the values of VSD and VDS have changed. So junction capacitance for N will be Cj naught N by root under 1 plus 1.8 by V naught was 0.89 something, right? So the capacitance that we get for NMOS is Cjn is how much is it that we are getting? What is the value? Like if we write down 8.2 10 to the power minus 8, 879. 8.2 into 10 to the power minus 8 by root under 879. 1.8 by 879. It's what is the junction capacitance that we are getting for N? Whereas for P it will be Cjp naught by root over 1 plus 0 by 0.914. So it is Cj P naught, which was already 11.817. 11.817 into the power minus 8 into percent square. So what is the CJN that we are getting for this particular bias, 1.8 volts? What is the value? Yes, how much is it? So with the bias voltages, will the area change?
It will change, right?
Why it will change?
I mean,
No, I get it. So what you mean is that depletion widths will change.
absolutely.
Yes, but the area that we are considering are the area of surfaces, right? Depletion widths
Okay.
will be very small compared to those surfaces. No?
Negligible.
So, negligible.
It's not.
Yeah, so we can consider that the
No
area
change in
remains
area.
constant. There is no change.
Constant.
Yes. So we'll simply use these junction capacitance. Yes, what was the value for CJN?
Calculating.
Okay.
Is there anyone? from other
Nobody
side.
calculated it yet. Is it taking that long? Like, so this is 4.697 into 10 to the power minus 8 farad per centimeter.
It's a 6.76 into 10 raised to minus 8. Did anyone get it? CJ of M. I'm
CJM,
getting 6
how are you
with
getting
this value.
6 point with this value? 8.2 into 10
With
to the
this
power minus
8.2 into 10 raised to minus 8 upon under root 1 plus
1.8 by
1.85.
0.879.
Mm.
I'm getting 4.697.
Mm.
And I'm using a scientific calculator, so there are less chances that it might be wrong. But if somebody could cross check it again,
Anyone else? Under root 1 plus
4.69.
4.697, right?
Yes, ma'am.
Yeah.
1.0.
4.284 10 to the power minus 5
Mm.
plus 11.817 10 to the power minus 8 into, what is the area? 8.208.
It's 4.69. I'm really sorry.
Yeah.
I get it on my calculator.
This is 8 only. 8.208 into 10 to the power minus 8. So the total capacitance that you get again in femtofarads is 11.505 femtofarads. So this is the capacitance that we get for input of 0 and when we have output of 1 in an inverter. Now, and again the same circuit, the next problem is in the same circuit as before, assume Cox is 7.5 femtofarads. Cox dash is 7.5 femtofarad per micrometer square for both N and P. So Cox dash N, Cox dash P. Now the length and width of the devices are as it declared earlier. Assume the overlap capacitance between gate and drain, COVB, is also the same as that of source, which is 0.95 femtofarad per micrometer square, and input is 1.8 volts. So if input is 1.8 volts, that means output is 0, right? If input is 1.8 volts, what will be the output? Output will be 0. So what is the small signal increment capacitance seen looking into the input at the bias point? Give your answers in femtofarad. So first of all, what are the input capacitance that we will see? Consider that body and source are shorted. So if body and source are shorted, that means the capacitance that we will have is CGS, that is gate source. Then there will be CGD, capacitor. Again, there will be a CGD from this particular transistor and your CGS, right? So now you have CGS from first transistor, CGS from second transistor, CGD from first and CGD from second. Excuse me. Yeah. So what I was saying is, like we have these four capacitors which will definitely come into picture, right? Now, first thing first, so the capacitors that we have are CGD, CGS of both the transistors. And if we observe very carefully, like, okay, what is the behavior when your input is 1.8? So, what is the behavior of your transistors? Because if your transistor is in cutoff region, your capacitors are there in a certain way. But the moment, let's say, your transistor is in linear region, the capacitance values change actually. And if they are in saturation, again the capacitance changes further. So, because of that, it is very important to understand what is the operation, region of operation of your transistors to exactly calculate the capacitances. So here we have PMOS, NMOS. So this is basically an inverter. So how to find out at what particular input, what is the behavior of your two transistors? So we find it out through our VTC curve, right? That is the voltage transfer characteristics of your uh, inverter. So how does the VTC look like? VTC looks like somewhat this, right? To be very specific, let's say it goes down at 0. Yes. So this particular VTC is divided into multiple regions. So it is considered that in first region, like this region, N in cutoff, P in linear. Similarly, at this particular point, P saturation and also saturation. That is where the same equal currents flow through your both the transistors. Now, in this region, which is beyond, like when you give 1.8 volts to your input, your P actually goes to cutoff, because if you observe very carefully, your VSG is 0. So the moment your VSG is 0, that means your transistor is off, right? And your VD is 1.8 volts. So VDS and VGS are almost equal, and VDS sometimes is not actually like no. So what I was saying, no. VDS is 0, but ideally it is not 0. It is very small value. So that's why we say that NMOS is not cut off. So rather it is in a linear region with very small VDS. So that's why in this particular region, where your input is at VDD, your PMOS is like cut off, your NMOS is at linear region. And that is the region actually that we are considering right now. We are saying our input is 1.8 volts. So your PMOS is actually in cutoff and your NMOS is in linear region. So what will happen because of this? So because of this behavior, now if, like, first thing, for PMOS, since PMOS isn't cut off, there are two capacitors that are coming into picture because of PMOS, right? But if we observe very carefully, your CGS is 0. CGS is 0. Because your CG and CS both are at same potential. So CGS is 0. The only capacitance that you will get over here is because of your overlap, C overlap. That is the overlap between your gate and drain or gate and source. There is no CGS present. So your CGS is 0 plus C overlap of P. CGD, the capacitance between gate and drain, this capacitance is when it comes into your input side, it will become again, this capacitance will become as C overdrive of P. Now second, when we write it for NMOS, which is in linear region, in linear region your CG is, that is gate to source region, it is half of Cox plus overdrive capacitance, and similarly CGD, that is gate and drain, will be half of Cox plus C overdrive of N. So the capacitance, because of that overdrive or overlap will be there, and there is the capacitance because of your oxide. So these both will contribute. So in linear region, we consider half is being contributed to drain and half is being contributed to source. Whereas when the device is in cutoff, the only capacitance that can come into picture is your overlap capacitances. So the input capacitance in this particular proof will be CGSP plus CGDP plus CGSN plus CGDN, and which is C overdrive of P plus C overdrive of P plus half into 2 C of N plus 2 C overdrive N. So that is 2 C overdrive of P plus 2 C overlap of N plus C ox of N. So which is equal to, how much was the overlap capacitance for drain source? And it was so here this is 7 point Cox is 7.5 femtofarad per micrometer square into, now Cox, what is the area that your this capacitance will come into picture? So it is length into width of your transistor. Cox is where your gate is, right? What is the area of your gate? That same area will be corresponding to your Cox. So length was 1 micro of the device. Yes, length of the device was 0.18 micro, and width of NMOS was 1.8 micro. So it is 0.18 micro into 1.8 micrometers plus overlap area. Overlap area is, what is the overlap length into width of your transistor. So overlap length was mentioned like this. Capacitance is mentioned. Overlap length. The length of drain and source region is 0.18 micrometer, 0.18 micrometer. The length of the device is Okay. So here the overlap length is not given to calculate the area. That overlap length is required to calculate the area here, like for overlap capacitance, because how would you show your overlap capacitances? Let's say your gate is like from here to here, okay? So this is your gate oxide. So this region is your overlap region, which will give you your overlap capacitance. So to know that overlap capacitance exact value, not per unit area capacitance, rather exact capacitance. So you need to know this particular overlap length, and when you multiply it with the width, you will get the overlap capacitance. So here we can find the values in per unit area only, per unit area itself. So it is Cox is how much? 7.5 femtofarad. 2 into C overlap is 0.95. 0.95 plus 0.95 into 2. So what is the total capacitance that we are getting? What is the total capacitance that we are getting? 7.5 and 0.95. It is 11.3 femtofarad, right? So this is the total capacitance that we are getting, corresponding to our this per micrometer square, because this is per unit area capacitance. So now moving on to the next problem. In this problem, input is applied to the CMOS inverter such that the output is at 0.9 volts. Okay, so there is, so again, it is the same. The same inverter question here. Your V for the same inverter question, V in is 0.9 volts. V out is also 0.9 volts. Now at this point, GM is 3.2 millisiemens. GMP, GMN is 3.2 millisiemens. R naught P is 17.5 kilo ohms. R naught N is 17.5 kilo ohms. At this operating point, estimate the capacitance seen looking into the input of the circuit. So we have to ultimately find what is C in. When this is 0.9, this is 0.9, this is this is 0.9. Input of the circuit, give your answers in femtofarads. Assume that the devices are well beyond pinch off, and CGD of the both NMOS and PMOS are purely the overlap capacitances. Okay. So now if your CG and CD are both 0.9 volts. That means, first of all, your transistors are in like well beyond saturation. So pinch off has already occurred. So when pinch off has already occurred, so what will happen? First of all, your CGS of N will be Cox of N. CGS of P will be Cox of P. CGD of N. Now, since pinch off has occurred, so there won't be any oxide capacitance present over there, but there will be a capacitance which is the overlap capacitance. So it will be COV of N, and CGD again, it will be COV of P. And the small signal gain for this type of configuration, that is AD, is minus GMN plus GMN plus GMP upon R0 in parallel R0 P. So if you observe it very carefully, it is GM into R0 only, but since the GM will come because of both the transistors, as input is given to both the transistors, right? So GM will come because of both the transistors. And we know that CGD dash is 1 minus AD into CGD. This is because of Miller effect. So your CGD dash is 1 plus GMN plus GMP by R0 P parallel R0 N into CGD. This is the actual capacitance that we will see in input, right? So the total capacitance that will appear in input is CGD dash N plus CGD dash P plus CGS N plus CGS P, correct? So the total capacitance is Cox N plus Cox P plus COV N plus COV P into 1 plus GMN plus GMP upon R0 N parallel R0 P. So the value that we get is C total equal to 304.83 femtofarad. We solve this expression, we'll get the capacitance as 304.83 femtofarads. Okay. Now moving on to again next problem. This is problem 5. So in this figure, it is mentioned that the CS is 2.2 picofarad, CD is 1.3 picofarad, and RD is 13.1 kilo ohm. Small RDS, this is gate, source, drain. So small RDS is 21 kilo ohms. GM is 1.6 millisiemens. The overall transfer function of the circuit is to be computed. Use Norton method. What is the pole of the output impedance? Pole and the output impedance of the circuit. Okay. So now we know that these are the values. It is a, what type of configuration is this? If you observe this transistor, what type of configuration?
Common gate.
Common gate.
It is common gate configuration, right? So for this common gate configuration with these capacitances, and also like your output resistance is also mentioned. With this, you have to first compute the transfer function. That is one thing that is mentioned. And secondly, the main question is what is the pole in the output impedance of the circuit? So, first of all, output impedance you will look from this particular node, correct? Z. And Z, we know that it will be like in the form of R and C, correct? So, here the pole that we will have at this particular node is given by 1 by R into C. For any particular node, at any particular node, if you want to calculate the pole, how you calculate? It is 1 by R into C. So the total resistance from that particular node and the total capacitance from that particular node, when you multiply the two and take a like reciprocal of it, you will get a pole. So for this particular question, your pole, I should better write it, pole will be 1 by R into C. So it is R out into C out. So for this node V out, how would you write R out? R out is RD parallel small r RDS, right? For this particular node, RD equal to like R out equal to RD parallel small RDS. And what about the C out? C out is CD, but nothing else has been given, like internal capacitances are not given, so we would not consider them. So we'll only consider CD. So the value of pole is 1 upon RD parallel RDS into CD. So this will become 1 upon RD into RDS by RD plus RDS into CD. That is RD plus RDS by RD into RDS into CD. So it was 21, 13.1, 21K plus 13.1K by 21K to 13.1K into CDS 1.32 farad. So the pole value is it is 95.35 mega radians per second. So the pole at your output is 95.35 mega radians per second. But the question is, okay, here it was asked like directly what is the output impedance, like pole at the output impedance node. So that is fine. But let's say if it would have asked like what is the value for your dominant pole, then which pole would be dominant? So first of all, how many nodes are there which are like AC nodes in this particular circuit? There are two AC nodes, right? A and B. So
Yes.
there are two AC nodes, and corresponding to these two AC nodes, you will see two particular poles. Now the question is, where, which pole would be dominant? So the dominant pole means the dominant pole that appears first is dominant pole. The pole that appears first is a dominant pole. Now, how would a pole, like what is the value of pole? We have already said that pole is okay 1 upon RC. So higher the value of R or higher the value of C will lead to smaller value of pole. That means when we draw a Bode plot or frequency response plot with frequency versus gain, and we place our poles over here, right? So the pole that appears first is the dominant pole. And this pole that appears first will have higher value of C and higher value of R. So the node where you have higher value of equivalent R and higher value of equivalent C, and that product is also high, then you will get the dominant pole. So if there are multiple AC nodes and you are asked to find the dominant pole or dominant pole frequency, so what you will do, you will find the like resistance and capacitances at each and every AC node. You'll calculate the pole value, and then you will find out that the node where you have higher resistance or higher capacitance will give you the dominant pole. But rather than going for like calculating, you can already go for like the basic idea that you know that for drain node the resistance is very high, and for source node the resistance at source node is very low. So from that it gives you the idea that okay, drain node will always have higher resistance, and drain node will introduce basically a dominant pole. Okay, so you don't have to calculate it multiple times. So yeah, that's all for today. Like these are the problems that we have for today. Any doubts?
Ma'am,
Ma'am, you are not considered the 2.2 picofarad resistance of capacitance?
Yeah, because we are only talking about output node, and 2.2
Okay. Fine. Thank you. Thanks, bro.
Yeah.
Yeah, you're right.
Any doubts?
no, at B node it is 1 by GM into CS, ma'am, pole.
Yes.
Is gate terminal capacitance and the junction capacitance same, ma'am?
No, I didn't get to your point. What are you saying?
How said gate capacitances and junction capacitances
Yes.
are two same, ma'am?
No. So gate capacitance is because of the gate's influence, and junction capacitance is formed wherever there is a PN junction. So junction capacitance is between, let's say, your source and substrate, your drain and substrate. That is where your junction capacitances will appear. Whereas gate capacitor appears between your gate and substrate, and overlap capacitance appears between your gate and source and drain and source. But it is not between two materials or where the junction is formed, I would say. So that's how these two capacitors are different. So junction capacitance is formed where you see a junction forming, which is a junction between, let's say, PN or any type of junction which is formed, like N plus N, P plus P. These type of junctions are also junctions, right? So in those places, that capacitance that is coming to the picture, we call it as a junction capacitor. But when we say gate capacitor, it is because, like in case of gate, what happens? So there is a metal, there is an oxide or an insulating layer, and there is another layer where you introduce charge. So what it forms is a parallel plate capacitor sort of thing. So that's why the analysis of that gate capacitance is also different from that of junction capacitance. Getting my point. That's why when I said gate capacitance, I only wrote down as like, can you mute yourself? There is a lot of noise. Yeah. So what I'm saying is, in gate capacitance, it behaves as a parallel plate capacitor, and we analyze gate capacitor as a parallel plate capacitor. Now, when there is a junction capacitance, there we introduce the concept of PN junction, and from there we deduce the capacitance. So both are capacitances, but their behaviors are different. Like one is a parallel plate capacitor, which is because of gate. But the junction capacitor is because of the junction that is formed and how the dq by dv is changing with respect to that junction. So that's why these two are very different from one another. They are not same. They are different. Is there any other doubt?
No, Pavani, madam, these capacitance are defined as a distance. I mean, two conducting plates separated by dielectric.
See, that
Right?
is only possible when you have like parallel plate capacitor behavior, right?
Okay.
But parallel plate, in case of junction, there also ultimately we come to the point where we consider, okay, like the depletion region is devoid of charges, and there are charges only on the other sides, on the two sides of the junction, and then we calculate the capacitance.
Now,
But
this capacitance, ma'am, is indirectly inversely proportional to the distance between the two plates. Correct?
that is always there.
So, if the depletion region decreases, and because of depletion region, the distance between the two conducting plates, or say two conducting material,
Uh,
uh, decreases,
yes.
the
So the
capacitance should increase, isn't it?
yes,
Okay.
it will increase.
So primary capacitance is primary depends upon the charge on the two plates and the distance between inversely proportional distance between the two plates. Correct? Charge on the two plates. I mean, separated by dielectric.
Yeah, it is
So
ultimately
you can vary the capacitor either by varying the distance between the two plates or by changing the charge on the two plates.
uh,
Compare. I mean proportion to each other.
so yeah, so you can say it like, let's say you are applying same amount of potential, but your charge is changing differently. So
Yeah.
that is ultimately dq by dv. So you will get the capacitance from there.
Yeah.
Or if you talk in like from the equation point of view, so it is epsilon a by d, right?
Yeah.
So, like if you change the dielectric material, then also you will change your capacitance. If you change the area, you will change your capacitance, as well as the distance between the two plates will also affect your capacitance. So, like you can think of it like dq by dv. So that is also capacitance. And if you think from very like basic formula of parallel plate capacitance, so there it is epsilon a by d. So you can go either ways and like explain your problem, like how you are looking into it and what is the basic factors which are changing,
Madam,
so that
C
you can
is
address.
equal to K into Q1 Q2 upon D square. Correct? K is the
Sorry.
constant of proportionality. C is equal to
Huh.
K into Q1 Q2 upon D square
So
divided by D
that
square.
is the formula for force, right? K Q1 Q2 upon R
Q1
square is.
Q2 are the charges on the plates. Say Q1 Q2 are charges on plate. D is the distance between the two plates separated by dielectric or an insulating material, SiO2 or whatever you call it.
Yes. No, so the formula that you are saying K Q1 Q2 upon R square
No,
is
D square, madam. D square.
D square. It is basically the
Force between two
force
charges.
between the two plates. That
Okay.
is the formula for force.
Okay. Force. Okay.
Yeah, it is not for capacitance.
Ma'am, second question.
Second question.
What we have exactly calculated on? Can you show in picture, ma'am?
Second question. Where is the second? This one.
Yes, ma'am.
So here, see, what we have ultimately calculated is the junction capacitance as we did in the first question. Here also it was asked like what is the total junction capacitance. But what has changed is the condition of your input and output. Earlier the condition was that your input is at how much? 0.9 volts. I guess your output was at 0.9 volts, right? In this particular question, first question, yes, your output is at zero point 0.9 volt. There was nothing mentioned about input. But in the second question, this was mentioned that your input has like input is at 0 volts, and we know this is an inverter, so output will be VDD. So now when your output potential changes, it ultimately changes your VDS or VSD, and because of which your capacitances actually change. So that's why we change the capacitances based on your applied potentials, and hence again calculated the junction capacitance. That's it.
It's between VDS, ma'am. NMOS of
Yes.
VDS. We have to.
Yes. NMOS,
But we
because
have
in
taken
PMOS there
total.
won't be any VSD, right? Junction capacitance has its like junction capacitance will be influenced by your applied potential, correct? And that formula is given by this particular formula of Cjn is equal to Cj naught by 1 plus root under 1 plus VDS upon Vn naught, correct? Now here, if your like applied voltage is 0, so you will get junction capacitance equal to Cj naught. But if you have certain applied voltage, that is VDS or VSD, your value of junction capacitance will change accordingly. Correct?
Yes, ma'am.
So that's what we have done here. Clear?
Okay, ma'am.
Any other doubts? Okay, so if there are no doubts, maybe we can break over here and meet next week again. So that's all for today's session, everyone. Thank you for joining. Have a wonderful evening ahead. Bye.
Yeah, thanks for your time, ma'am. Thanks for time and guidance. Thank you.
Thank you.
Thank you, ma'am.
See you all next week.
Yeah, thanks, ma'am.
Ma'am.